Welcome to this module, Remotely Sensed Data Acquisition. I will start this session with examples as to how the satellite sensors miles above the Earth are making a global effort to combat the coronavirus pandemic that can be presently seen unfolding at a rapid and dramatic scale. Tracking the effects of the virus from space can help institutions understand the pandemic without sending people into harm's way, and it can promote transparency in its efforts to combat the virus. Now, let us see what is happening in this image. A satellite has been tracking the construction of new hospitals and medical facilities in China as the cities try to treat an influx of patients. So here there is a huge demand for satellite imagery showing manufacturing and infrastructure in particular, particularly in the hard-hit parts of the world like China. So this is an image of a hospital in Wuhan, China, where images have been taken in 2017 and 2020. Now, satellites have also been taking photographs before and after photos of airports, bridges, and other locations to show how social distancing efforts have cleaned or cleared the roads and tourist destinations around the world. This particular image shows the Miami Beach in 2019 and an empty Miami Beach in 2020. The image at the bottom is the image of Qumran as captured by the Copernicus satellite and the Sentinel-2 sensor on February 27th, 2020. Here, if we analyze the image, it appears to have a large pile of lime. Lime is a substance often used to manage odor and decay in dead bodies. The image here signifies the country is using lime for its coronavirus victims who are being buried in a mass graveyard. Thus, the satellite images also provide a view that can't be seen from the ground and plays a big role in disaster relief. Now, if we see this particular image, it says that the air above China has cleaned up faster than ever before. Now, this is the dramatic effect of coronavirus lockdowns as seen from space. The new coronavirus impact on China is so severe, as it seems from the image, that it can be seen from space as a dramatic drop in air pollution according to the satellite data. The instruments that are on board the satellite are designed to monitor air quality that has picked up a substantial drop in concentration of nitrogen dioxide pollution since January 2020. Now, NO2 is a harmful substance emitted by gas vehicles, power plants, and other machines. So this decline is most likely related to travel restrictions in China since the virus became widespread. So this particular map shows the variation of nitrogen dioxide concentrations over China in January and February 2020, intercepted by the Tropomi instrument on board the Copernicus Sentinel-5B satellite. The first step in remote sensing is collection or acquisition of data with the help of sensors that are mounted on the satellites or that may be airborne, mounted on aircrafts flying over the region. Now, what are sensors? Now, in remote sensing, The device used to acquire data, that is, to measure the radiation arriving to the satellite instrument, is usually referred to as a sensor. It refers to a broader way of getting information than a camera. Remote sensing involves many different kinds of radiation in the electromagnetic spectrum. Satellites are very common platforms used in remote sensing. They carry a great diversity of sensors, often specialized to observe specifically the weather, landscapes, or natural disasters, vegetation. And some sensors are even capable of seeing through clouds or acquiring imagery at the night. Now, how do we categorize these sensors? Now, say if a sun disappeared, which type of sensor would miss it most? Would it be a passive sensor or an active sensor? A camera is a very common example of active and passive sensor. When a photo is taken without using a flash, the camera is detecting and recording natural light that is reflected off various surfaces. When a flash is used, the camera becomes an active sensor, detecting and measuring the light from the flash as it bounces off various objects. So, passive sensors are used to record an object's natural radiation, such as an infrared camera that records heat coming out from a rock formation, an airplane flying over a rainforest that registers the sunlight reflected from the forest. Now, the most common type of passive sensors include different kinds of radiometers and spectrometers that measure the intensity of electromagnetic radiation. And active sensors, on the other hand, are devices that sends out a signal in order to gather information about an object, such as a ship that sends sonar waves to scan the ocean floor uses active remote sensing, as do satellites that monitor hurricanes. Now, LiDAR is an active sensor which is used for surveying that measures the distance to a target by illuminating the target with laser light and measuring the reflected light with a sensor. A LiDAR system measures the time it takes for emitted light to travel to the ground and back and calculates the distance. It is most commonly used to make high-resolution maps with applications in geomatics, archaeology, geography, geology, seismology, forestry, and so on. Nowadays, this technology is also used to control and navigate autonomous cars. There are radar systems that are active sensors. Radar systems emit microwave radiation using a series of pulses from an antenna where the energy reaches the target. Some of this energy is reflected back towards the sensor. This backscattered microwave radiation is then detected, measured, and timed by the sensor. So many active sensors operate in the microwave portion of the electromagnetic spectrum. This makes them able to penetrate the atmosphere under many different kinds of conditions, such as the precipitation radars and the cloud profile radars. Then we have sonar as an active sensor that uses sound waves to see the water. Now, the short form sonar represents sound navigation and ranging and is helpful for exploring and mapping the ocean because sound waves travel farther in the water than do radar and light waves. Scientists primarily use sonar to develop nautical charts, locate underwater hazards to navigation, search for and map objects on the seafloor, such as shipwrecks, and map the seafloor itself. The remotely sensed sensors capture images that are hyperspectral, multispectral, or panchromatic in nature. Now, as this session involves dealing with images, so we will mostly discuss the sensors that are involved in capturing data in the form of images. We have multispectral sensors that capture multispectral images. So we start with multispectral imagery. They generally have 3 to 10 bands. An example of multispectral image, the image that is captured by Landsat satellite, images that are captured by Sentinel, images captured by LIS-3, LIS-4, which are Indian satellites. There are numerous multispectral sensors capturing multispectral images. In this particular image, we see that the images have been taken by the Landsat 8 sensor satellite, and they were acquired before and after transportation networks, and most business activities were shut down in a province of about 60 million people. Now, here we can see how the highways and metropolitan areas grow dimmer after the lockdown period due to the coronavirus impact. The detailed images here focus on the lighting changes in the Jianghan district, a commercial area of Wuhan in China, and nearby residential areas. These images have been nighttime images, have been taken by the Landsat 8 satellite. This are one of the series of Landsat satellites. Another multispectral imaging sensor is the MODIS, which is a key instrument aboard Terra and Aqua satellites. So Terra MODIS and Aqua MODIS are viewing the entire Earth's surface every 1 to 2 days, acquiring data in 36 spectral bands or groups of wavelengths. Now, this data helps to improve our understanding of global dynamics and processes occurring on the land, in the oceans, and in the lower atmosphere. Now, these are the image on the left is an image acquired by the MODIS sensor in 2020, which shows clear skies over the Caribbean. And the image at the right-hand side is a Landsat 8 image, which has captured images of a volcano eruption in Mount Sakurajima, Japan. Now, Sentinel data, which are a fleet of satellites designed specifically to deliver the wealth of data and imagery that are central to the European Commission's Copernicus program. And this unique environmental monitoring program is making a step change in the way we manage our environment, understand and tackle the effects of climate change, and safeguard everyday lives. Sentinel 5P, this is the image intercepted by Sentinel 5P. So in these images over India uses the data from Sentinel 5P, and they show that the average nitrogen dioxide concentrations from 1st January to 24th March 2020 and 25th March, that is the first day of the lockdown period in India, to 20th April 2020, compared to the same time frame as last year. And we can see how the nitrogen dioxide concentration has gradually decreased with time from March to April, and how the variation is visible if we compare the data with that of 2019. Now, next is the data acquired by hyperspectral sensors. So, the data sets or the images that are captured by hyperspectral sensors are generally composed of about 100 to 200 spectral bands of relatively narrow bandwidths varying from 5 to 10 nanometers. Hyperspectral imagery is typically collected as a data cube with the spatial information collected in the XY plane and spectral information represented in the Z direction. And at the right hand side, we can see an image of Mount Fuji, Japan, that was acquired by the hyperspectral sensor called Hyperion. And we can also see the vegetation spectral profile or reflectance. In 1994, NASA launched the first hyperspectral satellite called the TRW Lewis. But later on, in 2000, NASA launched the EO1 satellite, the Earth Observatory 1 satellite, which carried the hyperspectral sensor Hyperion. It was the first hyperspectral sensor from space. Hyperion collects 242 unique spectral channels ranging from 0.357 to 2.576 micrometers with a 10 nanometer bandwidth with a spatial resolution of 30 meters for all the bands. So there are other hyperspectral sensors such as Proba, Prisma. There are some sensors which are going to be commissioned such as NMAP, Hisui, HiSpiri. So there are hyperspectral image data that are generated from airborne sensors such as the Aviris, which has a spatial resolution of 5 meters and the spectral resolution of 5 nanometer interval. So these are images of a hyperspectral data cube that has been captured by the Hyperion sensor. This is an image captured by the WorldView sensor. So we have the WorldView 2 sensor and WorldView 3 sensor capturing images of Syria, where we can clearly see the difference in spatial resolution of both the images. The images or the clarity of image data of WorldView 3 is much better than. Now we come to the Indian satellite sensors. There are multispectral sensors and panchromatic sensors that have been launched by the Indian Space Research Organization. Recently, an advanced Indian satellite, Cartosat-3, has been launched. That is the third generation advanced satellite and has a very high resolution imaging capacity. Now, it is a panchromatic, multispectral, as well as a hyperspectral satellite, all of which very helpful in boosting the quality of images that it captures. So in Cartosat-3, multispectral indicates that the satellite can see in 3 to 10 bands of the electromagnetic spectrum. In this particular case, the multispectral resolution is, the spatial resolution is 1.13 meters. In hyperspectral range, the satellite's, the spatial resolution is 12 meters. Where Cartosat-3 stands out is in its panchromatic resolution. So here, Cartosat-3 has a ground resolution of 0.25 meters. This means that the satellite can pick out an object that is 25 centimeters long in an area. So it is the highest resolution camera ever built by ISRO and is the best panchromatic resolution camera in orbit today, known commercially. So it replaces WorldView 4, an American satellite, with a resolution of 31 meters. So when we think of handling these image data acquired by different sensors, we need remote sensing software to be able to read the data. They enable generating geographic information from satellite and airborne sensor data. So the remote sensing applications read specialized file formats that contain sensor image data, georeferencing information, and sensor metadata. So some of these software, the popular software have been mentioned here, some of which are open source in nature. So this is all in today's session, and we will move on with details about the resolutions, the spatial resolution, spectral resolution, temporal resolution of the image data acquired in the next session.